Okay, so this is another typical type of potential energy problem. The question is how much energy is needed to bring a particle of charge 2q to point P. Now we're going to assume that this charge and this charge are somehow locked into place, that somebody else brought them to this position a long time ago and we don't need to worry about it anymore. I'm going to assume, also I didn't write it, that these distances are both r, so these are the corners of an equilateral triangle. So what we're going to do is we're going to bring in this particle from an infinite distance away. So we're going to assume it's nice and happy off at infinity, and we bring it in. Now because this particle has a charge of plus 2q, that means that it will be repelled from these guys. So when it's an infinite distance apart, it's just chilling, it's fine. But as we bring it closer and closer, the total amount of energy in the system is going to increase. Now, once again, we don't need to include the amount of potential energy in this interaction between these two positive charges for this particular problem. There's another type of problem where we would have to consider all three of these interactions, but we're not doing that problem. Okay, so the amount of energy required to bring a point in has to do with the amount of electric potential energy. So remember, at infinity, we've done no work. So the potential energy, the EPE of the plus 2q charge is 0. Okay? But we're going to bring it to this location at the tip of this triangle. So I'm really doing two things. I'm bringing this charge in towards this point, and I can compute the amount of EPE added to the system by doing so. And then I can compute the amount of EPE required to bring the charge in towards this point. And superposition says that I can do the calculation separately and combine them at the end. The fact that these two charges are already together doesn't change the amount of energy required to do this. So the amount of work we would have to do is going to be the EPE at point P. So we're now looking at point P. Okay, so the work that we did is equal to the change in electrical potential energy. So that's going to be K, and then we multiply the charges. So this is plus Q and plus 2Q divided by the final distance. Okay, so because we're choosing infinity as our 0 mark, and because we're bringing them together, the amount of work we do just depends on the final distance. Now notice that because we're dealing with energy, which is a scalar, we don't have to worry about directions at all. There's no vector nature to this. Now this was the amount of work we did to bring the charge towards the 2q charge towards this particle. We also need to factor in the amount of charge. Now from the symmetry, because this point is equidistant from here and here, I'm just going to have to add in exactly the same thing, plus q, kq, 2q over r, and then I add everything all together and I get 4k q squared over r squared. Now, if we were asked, and this is a different question, what is the total EPE of this system, then what we'd have to do, oh, that's a question. What we'd have to do is say EPE total is equal to the amount of EPE in charges 1 and 2 plus the amount of EPE in charges 2 and 3, plus the amount of EPE in charges 1 and 3. For a system of 3 charges, we'll need to add up a total of 3 potential energies. If I had a system of 4 charges, then I would need to do 1, 2, 3, 4, 5, 6 calculations to get the total potential energy in the system. If I were asked how much energy would be needed to bring in a particle to complete a quartet, so let's say that I have these 3 particles already in place, and I'm going to bring in another particle. Hello. Then all I would have to do is calculate the amount of energy gained by this interaction, this interaction, and this interaction. So doing a problem like this, you need to be very clear. Are we bringing one particle in to a pre-existing system, or are we being asked the total amount of energy in the whole system? Okay.